This is a very key subject in terms of laying the foundation for what we're going to be discussing over the next day or two. So why do we need to deal with uncertainty during tailings characterization? Are all the results that we're getting good quality and reliable? And the answer to that is generally no. So what are we doing about it? How do we get better information so that we can put together reliable designs and check reliable performance of our tailings dams? So I'm going to talk to some of the key aspects to tailings characterization. So why do we deal with uncertainty? Ultimately, we've got to come up with something related to slope stability that we can believe in, that we can trust in, and that we can make sure that the public is protected in terms of dam safety. And there's uncertainty in terms of the input parameters to our slope stability assessments, and particularly if we haven't done enough tests. Statistically, if we've only got 5 results, that's not going to be sufficient. So how do we make sure we've got enough results and that they're good quality? And there's the process in terms of that diagram at the bottom there. In terms of our tailings characterization, that feeds into the site geotechnical model, the SGM. So we have to go out and we have to model the site. We have to do all our foundation investigations. And generally with a new tailings dam, you've got the opportunity of doing that up front. And there's no excuse for not getting good geotechnical data at the beginning of your project. If you have to come back later, it's a lot harder and a lot more expensive. And then you put together the geotechnical design model, which then incorporates the foundations plus the structure on top of it. And that then feeds into your stability analysis. So that's the model that's been put together in terms of the ICOLD Bulletin 194. It suggests that you follow this process. So it's not a standalone process. It obviously has to feed into the slope stability analysis, and it's dynamic. Your tailings dam is not a static structure. A water dam typically is designed, built, and it's more or less a static structure, apart from the water level rising and falling. Tailings dams are not like that. They keep changing. Your ore body can change. The process plant processes can change. And then your deposition practices can change. And so all of that affects the behavior of the facility, and what you designed up front may be quite different from what actually gets built and what you have to evaluate in terms of performance. So in terms of the ICOLD Bulletin 194, you need to do geotechnical classification, geochemical classification, and that includes then a range of lab testing and in situ testing. So in terms of the geotechnical classification, obviously you need to take a number of samples, both from the foundation and from the tailings, but up front in the design, that's not so easy to do. And you've got to make sure that you cover the variability of the site. Foundations can be quite variable, as you know, in a valley, as opposed to the areas you've got, whether it's transported soils or residual soils, and obviously there's faulting. And you need to understand how that all affects your performance of your facility. In terms of the samples tested, are you doing the right tests as part of that geotechnical characterization? In terms of geochemical classification, again, you've got to take a range of samples and they've got to be representative. And that may change over the life of the facility as well. So make sure that you understand what's coming from the ore body, not just in terms of geotechnical properties, but also in terms of geochemical classification. And Duthe is going to talk to us in a bit more detail about that a bit later. In terms of lab testing and in situ testing, you need testing programs. The lab testing should reflect the type of tailings you've got. Our tailings can vary quite substantially from a copper operation to a gold operation to a platinum operation to an iron ore, bauxite, or mineral sands. Some of them have got clays in them that behave very differently to those from just a hard rock grinding tailings. So we need to make sure that we're doing the right testing in that, and particularly when it comes to in situ testing as well. Are you doing the right tests in the field and getting representative samples? So when it comes to the design of a tailings facility, how are we going to address the uncertainty in the geotechnical design model? may not have good samples of your tailings. You should be able to do good foundation investigation right up front. It's always possible to come back and do more, but it's best to get that done properly up front. If you haven't got reliable samples, what are you going to design to? We shouldn't be in that situation where a client is telling us, oh, just assume the tailings behaves like the mine next door. We used to do things like that. We can't do that anymore. We shouldn't be accepting that. We should be getting to a point of reliable information for design purposes. And yes, if it's not a fantastic range of samples that you've got up front, during the performance stage, during the construction phase of the tailings dam, you've got the opportunity to keep testing, keep gaining knowledge, keep building that database. And that comes later. So obviously your stability analyses up front for design, that's what you've got. You've got the information you've got, you do the best you can with that information, but you've got to keep checking that during the operational phase. In situ testing is a very, very, very valuable tool for us to go in and every 2 to 3 years keep doing further testing. So it's not just index testing, but it should be shear strength and other forms of testing that help us. And we should be correlating the probing tests with lab tests. So relying just on probing tests is probably not enough. And you'll hear more about that during the coming day. And then, of course, keeping on updating and running stability analyses as you get that new information. And keep tweaking it and checking that your design is performing, and if it's not, what remedial measures might you need to take? And you've got to keep communicating that with your client. So the last couple of things in terms of this subject, and this is the last slide, is 5 to 10 years ago, we might have been happy with doing 10 triaxial tests and maybe 30 or 40 index tests. It's unlikely that that's sufficient anymore from a statistical point of view. You just haven't got enough information. You haven't got enough reliable information. And when you look at the consequence classification of structures that we're dealing with, if they're in that very high to extreme, you've got to put together a robust design that doesn't just last the life of the operation, but lasts well beyond that, especially if it's not going to be remined and it is closed as a structure. So how do we get that information? Now we should be in a position where we're asking for enough testing that we've got sufficient triaxial tests that we've got critical state lines, that maybe we're taking into account cyclic shear testing as well. So whatever it is that's related to your structure, you should be getting sufficient information that you've got reliable information and you can produce a robust design. And the same with the in situ testing. We were happy 5 to 10 years ago just to do some probing and some dissipations. Now we're being asked to do seismic resistivity probing as well. We're asked to do field shear vein testing because it helps us, but sometimes it might be the wrong test. We're doing dilatometers as well. And then there's a whole lot of question marks around what sort of samples are we getting? How representative are those samples? Is a MOSTAP sample sufficient? What can we use that for? If you have to remold that sample, how representative is that? Or do you need to be getting Shelby's and piston tube samples, higher quality samples? And we'll even hear about freezing of samples later today, so that we're not losing the fabric and the stress history that's built up in those samples, particularly in the tailings. So these are things that we have to start looking at in terms of reliability and uncertainty. And I'm going to end there because I think I've laid the foundation for what you're going to hear about later today. Our next presentation is going to be given by Torres Cruz. Many of you have come across him or know him. Luis has been at Wits for, I think he was here for between 8 and 10 years. Lecturing. Luis, you online? Luis has now moved to
Yes.
University of British
Yes,
Columbia. He's based in Vancouver. And so he's certainly very capable. I'm going to hand over to him. And if you can pick him up. There you are, Luis. Thank you for joining.
Yes.
I know it's quite late in the evening for you, and you'll be speaking through into the early hours of the morning. But thank you for joining us. Thanks for your contributions, and you're welcome to introduce yourself further in terms of your role. And over to you for the title of your next presentation, or your first of 3 presentations. It's on geotechnical classification. Thank you very much.
Thank you. Andrew, can you confirm that the slide is showing on your side now? Can you see my slide?
Not yet. We can see your photo, your video.
Okay. Just one second. Yeah. Can you see it now?
Yes, we can. Maybe if you can shift it, that's great. You're all set. Oh, thank you.
Okay, brilliant. And I'll just... Perfect. Good morning, everyone. And thank you for the introduction, Andrew. As Andrew mentioned, I was for almost 16 years at the School of Civil Engineering and Civil and Environmental Engineering at Wits University. Recently, I have relocated to the mining department of the University of British Columbia here in Vancouver, Canada. So my first presentation is going to be on geotechnical classification, which is item 6.2.2 in this bulletin 194 that was recently issued by ICOLD. And I want to begin by pointing out that the bulletin touches on 2 types of classification. One is geotechnical and the other one is geochemical. So in this presentation, I'm going to be addressing the geotechnical side, and shortly after my presentation, Duthe will be addressing the geochemical classification. So let's get into this. The bulletin makes us aware that we begin with obtaining physical and index properties that include particle size distribution, Atterberg limits, particle density, which can be expressed either as the density of the solids or as a specific gravity. And it also explicitly mentions limiting void ratios, that is the minimum and the maximum void ratio. Further to these physical and index properties, the bulletin also mentions that for existing tailing storage facilities, one should aim to establish values of water content, the dry density, and if you have the dry density and you also know the specific gravity of your solids, then you can also calculate the void ratio and also the degree of saturation. Now, what do we do with this information once you have that? What use can we make of it? There are 5 tailings type categories addressed in the bulletin, going from coarse over here at the top to ultra-fine tailings over here at the bottom. So we can imagine that this will be our more permeable and less compressible material, whereas this one over here at the bottom would be the less permeable but more compressible material. So here we have some broad descriptors of each of these 5 categories, and we are also given some reference or indicative particle size distributions of where these might fall. Coarse tailings, hard rock tailings, altered rock tailings, fine tailings, and the ultra fine tailings. So that's in terms of particle size distribution, but there is also guidance in terms of Atterberg limits. So if we plot on the traditional plasticity index versus liquid limit chart, we get indications of where we expect each of those 5 categories to fall. I really, really like that the bulletin explicitly puts the emphasis not on classifying, but on predicting behavior. And I quote the bulletin here. It says that these 5 types of tailings constitute a useful framework for predicting general behavior. In other words, the bulletin is reminding us that classification is a means, not an end. And to drive that message home, I really like this quote from the soil liquefaction textbook by Jeffries and Bean, which says, "It really does not matter if a stratum is called silty sand or blue cheese with holes. What matters is its mechanical behavior." So all these index properties, we are not after them in themselves, but rather we are trying to establish or we are trying to make initial estimates of engineering behavior based on those index properties. And the way we make those initial estimates is by making use of previously published correlations. So let's see what sort of estimates we can make. So I will begin here with this graph from a 2018 paper that is showing permeability in units of centimeter per second on the vertical axis and void ratio on the horizontal axis. And the first thing that stands out from this graph is showing just how permeability, considering all types of soils, permeability can easily vary over 12 orders of magnitude, which is quite something. The other thing that we see in this graph is that permeability is not uniquely correlated to void ratio, right? At a void ratio of 1, your permeability can be as low as 10 to the negative 10, or it can be as high as 10 to the negative 1, depending on the size of the particles. But more strictly speaking, it's not really the size of the particles that is controlling permeability, but the size of the pores between those particles, which is, of course, a related concept, but it's not exactly the same. One thing is the size of the particles, another thing is the size of the pores. The other thing that this graph reminds us of, and let me use as an example these red dots over here at the bottom, is that for a given soil, in other words, for a given particle size distribution, the permeability is not constant, which makes perfect sense because the void ratio at which that soil exists is going to control the size of the pores in between the particles, and therefore it will have an effect on permeability. So if we really want to have a unique correlation for different types of soils, a unique correlation which does not emerge in this slide, we would have to correlate hydraulic conductivity to the mean pore size as shown in this figure. Now, there's a lot of data from different sources being shown here, and there's a lot of scatter, therefore, but the correlation is quite significant. And I believe that this is the sort of correlation that one wants to use to get an initial estimate of what might be the hydraulic conductivity of the soil that you are interested in. And of course, you might be wondering, yeah, but this is in terms of mean pore size, which we don't ever measure. It's not really something that commonly gets measured in a soils laboratory test, agreed. But the authors have done something nice here for us, and they have given us two expressions that we can use to estimate what is that mean pore size. And that expression is given in terms of parameters that generally are measured. So for fine soils, that expression for the mean pore size is a function of the void ratio, of the soil, of the solid density, and of the liquid limit. And for coarse soils, the expression for mean pore size is a function, again, of void ratio and of some characteristic diameters that you can extract from the particle size distribution curve. So with that, you can make an estimate of your mean pore size and get an idea of what might be the hydraulic conductivity or permeability of the tailings that you are considering. So that was in terms of permeability. In terms of strength, there are correlations, for example, between effective friction angle and plasticity index. And what we are seeing here is that the higher the plasticity of a soil, the lower the effective friction angle that we should be expecting. And over here we have something similar, but this is effective friction angle in terms of relative density. And in this case, the authors have incorporated the effect of the confining stress level. Okay, so remember that the higher the confining stress level, the more likely it is that that soil will behave in a contractive manner. And therefore, if it is contractive, it will have a lower friction angle, and that is reflected in the trends shown in this figure. Here I am showing correlations between compressibility and a number of index properties or in situ values. So those values are natural water content, the liquid limit, the in situ void ratio, or the plasticity index, right? And agreed, there's a lot of scatter, but again, the idea is to use these correlations just to get an initial estimate of what might be the compressibility characteristics of your soil. So in this case, the authors are dealing with both the compression index and the recompression index, we might call it, where the compression index is the slope of this virgin compressibility curve, whereas this recompression index or rebound index is the slope of the compression curve of an over-consolidated soil. So there we go, CC and CR. This is a 2016 publication. There are older versions of those figures. This is from 1990. And again, we see the compression index and the recompression index expressed as a function of the plasticity index. And the message here is the same. Look, the greater the plasticity of the soil, then the greater the compressibility that you can expect to observe in that soil. Let me move on now to talk about the maximum and minimum void ratio and how they can be used as indicators of the critical state line parameters gamma 100 and lambda. So to start unpacking this, let's just start by reminding ourselves, what do we mean by Emin and Emax? So any type of soil can exist in a variety of densities, right? So any soil can exist either in a very loose condition or in a very dense condition. Theoretically, there should be limits on the density that a soil can attain. There is a limiting dense condition and a limiting loose condition. When the soil is in its loosest state, it will have reached its maximum void ratio. And when the soil is at its densest state, then it will have reached its minimum void ratio. So that's what we are referring to by Emax and Emin. They are giving us an idea of the loosest and densest conditions at which a soil can exist. Now, coming on to the critical state line, which I am showing here in this figure. So, and by the way, notice that over here I refer to it as the critical state line. Over here I'm using the abbreviation SSL, which stands for steady state line, because I am treating those two terms as interchangeable here. So I hope that's not confusing anyone. And we know that this critical state line, we generally draw it in two projections. One of the projections is the one that I am showing here, void ratio versus mean effective stress. And it is very common to assume, at least as an engineering simplification, that if the mean effective stress is plotted on a logarithmic scale, then the critical state line will linearize. And we take this critical state line to divide this space into a contractive area where our soils are prone to losing strength, and a dilative areas where the soil is not prone to losing strength. Now, as with any critical state line, we need two parameters to not as with any critical state line. What I meant to say is, as with any straight line, we need two parameters to define it. One is the slope, lambda, and the other one is an intercept, right? Except that if this is logarithmic, then you don't really have a zero value here. So you don't really have a y-intercept. So you need to choose any value at which to define that intercept. The most common selection is to assume that let's say the y-axis is at p prime equal 1. And we call that gamma 1 or simply gamma. For statistical reasons, I prefer to work with gamma 100. In other words, the void ratio at the critical state line when P prime is equal to 100 kilopascals, right? That's gamma 100 indicated there. So you're going to see gamma 100 in the slides that follow. And I need to say two more things about the critical state line. One is that this lambda depends on the base of the logarithm that you're working with. So if you're working with log 10, you get one value of lambda. But if you're working with a different base, I mean, the other common type of base is a natural logarithm, then that affects your value of lambda. And I'm going to show you just now how you can go from one base to the other. And the second thing that I wanted to say is that this defines the state parameter, right? The state parameter is essentially the distance between the state of the soil and the critical state line. So if it's on the contractive side, the state parameter is positive, and if it's on the dilative side, this state parameter, represented by the Greek letter psi, will be negative. Right, so there's a lot of interest in defining this critical state line, and to find it, you need to run a series of triaxial tests. So let's say generally you'll have to budget for about 10 triaxial tests, hoping that they will yield something between 6 or 8 useful points on the critical state line. So it is great if we have some index properties that tell us what to expect of the critical state line. And that's where these correlations can come in handy. So here I am showing a correlation between gamma 100 and the minimum void ratio. And the nice thing about this correlation is that it is based on a database of over 160 non-plastic soils. And here I need to emphasize that this is applicable to non-plastic soils. And the markers that are indicated here with color, those are tailings. And they follow the same trend as the non-tailing soil. So we know that this correlation is applicable to tailing. There's also a perhaps weaker correlation with Emacs, but although it is weaker, I think there's still some use in considering this. And over here, this is not so much, so this is now the correlation between the slope lambda and the minimum void ratio. There is much scatter, and I am suggesting this line saying that lambda is equal to E min divided by 3. But this is acting not as a best estimate of lambda, but rather as an upper limit, as an upper bound for what you might expect lambda to be. So let's say that your minimum void ratio is 0.4. So this is telling us that you should not be expecting to see a lambda that is higher than about 0.14. So that was for non-plastic soils. What about for plastic soils? Soils that do have measurable plasticity limits. So here we can use correlations, say from this one from 1968 in the original critical state soil mechanics textbook. Back then, Schofield and Roth were already pointing out that there is a correlation between lambda and the plasticity limit. But this is not the plastic limit in itself. It is actually the V, which stands for the specific volume at the plastic limit. And what is the specific volume? The specific volume is simply the void ratio plus 1. The other thing that I have to point out here is that this lambda is not based on a log 10, but it is actually using a natural logarithm. So it is a base 2.718 and so on. And this equation here is showing how you can go from a lambda calculated in a base 10 to a lambda calculated in some other base B. I have seen that there is a common misconception that lambda is correlated to particle size. In particular, that the finer your soil, the higher the value of lambda that you should expect to see in that soil. And that might be true for soils that have a significant amount of plasticity, as I showed in the previous slide. But many of the tailings that we are dealing with are non-plastic. And those tailings can have a fine fraction that still does not exhibit any plasticity. So in those non-plastic tailings, the data does not reveal any type of correlation between lambda and particle size, as I am showing in these two figures. So both these figures have lambda on the vertical axis, and on the horizontal axis, they have some sort of descriptor of the particle size, be it fines content or your median particle size D50. And regardless of the particle size descriptor that you are adopting, you don't see any type of correlation between lambda and that and particle size. So since I have mentioned that these limiting void ratios, E min and E max, are useful predictors of some critical state line parameters, it is also important to address, well, how can we measure them? How do we measure E min and E max? I know that South African geotechnical laboratories do not routinely measure them. And it's also not only a South African issue, because in general, the standardized methods to measure E min and E max are not designed for soils with significant amounts of fines, such as tailings. So whether you look at the ASTM or at the British standard or at the Japanese standard, you will see that their procedures to determine E-min and E-max are tailored for soils that have fines contents smaller than 5% or 15%, depending on which standard you are looking at. And of course, tailings, it very frequently have fines contents that exceed 15% by quite a wide margin. So what alternatives do we have? Well, I think we have at least 4 alternatives that we may want to consider. The first one is that although the standard is saying that you have to only use it on soils with fines content smaller than 15%, well, you can use it anyway, okay? And maybe it sounds a bit strange, but it's done. It has been done. There are quite a few precedents in the technical literature where you see that the authors are saying, look, our soil has a fines content greater than 15%, but there's no standard for that. So we're going to use this standard anyway. Okay, so that's one thing you can do. Another approach that you can take is to use non-standardized methods that have been documented in the literature, and there's a few of them, and this reference down here that I'm listing at the bottom mentions a few of those non-standardized methods. You can also use Proctor compaction, which is generally used to find the maximum density, but you would be using it to find the associated minimum void ratio for of that density. But the one disadvantage of trying to use Proctor compaction is that it requires a sample of about 6 kilograms. So that's quite a bit. And tentatively, you can also measure Emax and correlate that Emax to your E-min. And I'll show you how I am suggesting we do that just now. So let me touch a little bit more on these four alternatives. So this is the standard method to calculate Emax suggested by the ASTM. Essentially, you funnel your sand, because this is tailored for a sand, not silts, but you would use it for silts anyway. You funnel your soil gently into a container that has a known volume, and you try to establish the soil in as loose a condition as possible, in other words, as low a density as possible, and you determine the associated highest void ratio, or Emax, okay? And as I said, this applies only for fines content smaller than 15%, but you use it if there is no other alternative. Coming to the non-standard methods, I want you to keep in mind that if you use a vibrating table method, that has the disadvantage, in my experience, that it can lead to a significant loss of fines. So I don't recommend vibrating table methods. And as I mentioned, the Proctor compaction methods, well, they're useful and they produce good trends, but they require large samples. So you can consider using a non-standardized method like the one described in that reference that I showed a while ago. I also did this. I developed a non-standard method for my PhD thesis, and it's also described there in quite some detail. And this is the sort of equipment that I use to measure that E-min. And then the fourth alternative that I mentioned, which is that you can determine Emax and then estimate E-min as a function of Emax. That suggestion is based on this figure that I am showing on this slide. This is a figure from a 2002 paper, and it is showing maximum versus minimum void ratio for a wide variety of soils. that go from clean sands to also gravels, all the way to silty soils where the fines content can be as high as 70%, and the clay content can be somewhere between 5 and 20%. And all these soils have their Emax and their Emin determined with the procedures of the Japanese standard. And what emerges here is that despite the variability in soils, there is a very clear linear trend, and I hope you can appreciate it before I put it on the slide. There you go. This data is telling us that, look, roughly, if you let me say, if you're in a hurry and you need to make an estimate of what is your minimum void ratio, you can probably get close to the right answer by assuming that your minimum void ratio is 60% of your maximum void ratio. Okay, so I'll stop there with Emin and Emax. Let's talk a little bit about particle angularity, which is not explicitly mentioned in the bulletin, but of course, particle shape affects the mechanical behavior. So if you have measured particle shape, somehow you can make estimates about things like, for example, the critical friction angle. So this is showing that angular particles, in other words, particles that have a low degree of roundness, have a higher critical state friction angle than rounded particles. Okay, so particle shape affects your critical state friction angle, which we often call that slope M in the QP prime space. Okay. It's also good to be aware that generally, if your fines are non-plastic, then your particle size distribution does not affect the slope in the QP prime space. And here I am showing several examples. These are with platinum tailings, and regardless of the fines content, you get pretty much the same M. And these are tailings from the Scala tailings facility in Italy. And again, regardless of the particle size distribution, they are all falling on pretty much the same Q versus P prime line. Particle irregularity also results in higher compressibility, which I think makes intuitive sense. If we have particles with sharp edges and corners, then we can envision how those edges and corners are going to break as the stress level starts increasing, and that's going to affect the compressibility of the soil. And we must keep in mind that because many tailings are originated during a rock crushing process, then they will tend to be very angular, as we see here for gold tailings, for platinum tailings, and for copper tailings. And of course, using these correlations that we just looked at means that we need to be able to quantify particle shape somehow. And there are charts such as the one that I am showing here from 1963, which continue to be used to this day and offer very reasonable results and allow you to make fairly quick estimates of what might be of particle shape descriptors such as roundness or sphericity. Okay, so please don't think that, that quantifying particle shape has to be this very intricate and complicated process. Well, it can be if you want to get into details, but you can also use visual descriptors such as these to get a number assigned to your particle descriptors. The bulletin emphasizes that parameters estimated using the charts in Bulletin 181, which are charts like the ones that I've been showing just now, can be used for preliminary purposes, but do not replace the full characterization of tailings properties based on site-specific data. In other words, These correlations give you a first estimate of what you can expect from the actual advanced laboratory testing, but they do not replace that advanced laboratory testing. I also think they allow you to do quality control on the data that you are getting from the laboratory. Because if you have a rough idea of what to expect, then it makes it more likely that you can detect an anomaly in the results if such an anomaly exists. Then the question of how many samples, and that was also partially addressed by Andrew before me. Well, sufficient to characterize variability and uncertainty is what the bulletin tells us. And variability and uncertainty, we have a lot of in tailing storage facilities. So to show and to illustrate some of that variability, I am showing you here particle size distributions from multiple samples obtained from the same tailings facility. So on the left-hand side, these curves come from samples retrieved from a platinum tailings dam. And this one on the right-hand side, this comes from the Brumadinho dam, by the way. So that was iron ore. And you can see that there is strong variability in particle size distribution. And I think this highlights the value of those correlations with index properties, because your index properties are easier to measure and give you an idea of what are the properties that you can expect from each of these particle size distributions, whereas it would be completely impossible to measure, let's say, the critical state line of each one of these gradations. Right, my closing remarks is that geotechnical classification is a means, not an end. Please remember that blue cheese remark by Jeffries and Bean. Secondly, that we must take advantage of published correlations to determine the anticipated behavior of the tailings. By behavior, we mean, of course, the engineering behavior. And lastly, that there are simplified approaches to measure mean pore size, minimum void ratio, and particle shape. Right, and with that I close, and I thank you for your attention. Hopefully I'm on time.
Oh, thanks very much, Luis. And yeah, I think we can always keep learning from people like Louise. We're going to move on to the next presentation, which is from Duthe. She's going to give us a talk on geochemical classification, and I'm sure we will all benefit from learning a little bit of chemistry. Dai has a background in hydrogeology and has really taken to the geochemistry field, and it ties in very nicely with hydrogeology. So over to Dai. Thank you.
Okay, thanks very much. If I want to point, Andrew, you have to go to the screen. Okay, all right. Okay, thanks very much, everybody. So I'm going to try not to bore you with too much chemistry and put you to sleep, because I know that you're mostly tailings engineers, but I've got a passion about this geochemistry, and I hope that I can share some of that with you now. So, of course, we look at the classification of the geochemical classification based on the environmental concerns, and that also feeds into the GISTM, where there's no environmental harm. Okay, and of course the main concerns that everybody thinks or knows and is well familiar with is that we always look for acid rock drainage and metal leaching, and we use static and kinetic tests to get that metal leaching out. But there's also the total dissolved solids that we want to have a look at, as well as the suspended solids, and I will talk a little bit about that, and it kind of also feeds into the particle size that has been spoken about. And then there are also the fugitive processes, you know, the reagents during the processing, those all go out into the tailings, and those also create their own bunch of problems. And that includes cyanide, mercury, the SOxes and NOxes. But the whole thing is to prevent impaired beneficial uses to the communities, to the aquatic system. So that's the whole reason that we do that. Regarding the sample size, you know, you always want to get at least a few samples representative of different components of your tailings. And this is why this is an ongoing process. And Andrew referred to it as well, that when the ore body changes or when the processing changes, then you should be doing tailings geochemistry again, because it isn't a constant, it's not constant. So for example, you can see there's a pile of old tailings, but you can see all the layering and the fine settle out and the coarse grain settle differently. And we want to try and get an understanding of the geochemistry of all of those components, because don't forget, the finer the particles, the more reactive surface, the more you're going to change your chemistry. Okay, so I'm touching very briefly on acid rock drainage, which everyone knows and everyone is familiar with. But what I did want to point out here is that it's mainly to do with pyrite oxidation, but you get pyrite oxidation not only being exposed to oxygen, but you also get pyrite oxidation when it's submerged. If you've got a lot of dissolved iron in there, you're actually going to produce more acidity than just from your exposed on surface, your tailings on surface. So that's the first point about pyrite. And pyrite's a disulfide, so I'm going to talk about some of the other sulfide minerals as well. And then the next familiar term that everyone knows about is acid neutralization, and that happens when you get the weathering of your carbonates in particular. And that produces a lot of alkalinity, and that buffers the acid that is produced. It's a bit like taking your Gaviscon. Now, the thing about it's not only carbonates that can produce this buffering capacity. So when we look at you'll see why we want to go and look at the minerals, and that's because actually a lot of these minerals provide some buffering capacity. So if you look at the bottom graph, or the right column, if calcite, that obviously gives you the most buffering capacity, and quartz kind of gives you the least. But all of those feed into your whole mineral assemblage, and there's this whole sort of toxic soup, or not toxic, there's this whole soup of things going on, reactions going on in your tailings, the acidity being generated and the buffering capacity coming in. Okay, so that's how we come to defining whether you've got acid mine drainage or saline drainage or neutral mine drainage. Because you get a lot of other minerals, which are sulfides, but they have only one sulfide, they're not disulfides. And those release heavy metals, and they release sulfate, but they don't release necessarily acidity. So you get different fields, and that's how we really define whether you've got acid rock drainage, neutral mine drainage, or saline drainage, as a function of the pH, the sulfates that are released, and also the heavy metals. Okay, so that's why we need to look at mineralogy. That's the first thing. We have to have a look at what's in there, in the tailings, over the life cycle. And that's because you've got your primary and secondary minerals. So although it goes out as one thing, as it's sitting there weathering, you're getting secondary minerals that are precipitating out into your tailings. And these they're also mineralogical changes, as I mentioned, going from mining oxides to sulfide zones. You need to look at your mineralogy again because it's going to change. And then weathering of your minerals, that can also result in changes to the volumes of your tailings. Now that's important for the whole planning of the tailings. So for example, in kimberlite tailings that forsterite to serpentine, when it weathers out there, increases the volume by 40%. I mean, that's a big volume, and that, of course, has got more water in it as well, water retention. So, and there's also stability associated with swelling, clays, smectites. There's also the colloids, if you've got a lot of colloids in your tailings. So we look at mineralogy. We use different methods. Mostly it's XRD. That's the one we use the most. But there is also scanning electron microscopy. And there's just an example of some tailings, various samples from the overflow, underflow. So that's the point of looking at all components, the lighter minerals compared to the heavier, and size dependent. And then we look at whole rock analysis as well. So there's XRF, which is actually more commonly used for geochemical exploration, but sometimes when we really want to see what there is in there, it looks for the elements. So we're not looking at minerals now, we're looking for what's the bulk of the elements. But more frequently, to get the whole rock analysis, we do a total acid digestion. And that's how you can just basically throw a whole pile of acid at it and see really what is in there. And then you do an ICP scan to see what comes out. And that gives you your total concentration. And I'm going to tell you a bit later about total concentration because, of course, in South Africa, tailings is required to be classified in terms of our waste classification, and we need that TC, the total concentration. Okay, so then the next tests that we do are static base accounting. Now, these are rapid, they're less expensive than kinetic, but one drawback is they don't consider the rates of reactions. So, but basically, the lab gives you all these little, they give you paste pH, the sulfur speciation, so you want to know what's total sulfur as opposed to total sulfide from total sulfates. And then from that, you can work out your maximum potential acidity, which is basically the total sulfur times a factor of 30.6. Then your acid neutralization capacity is a titration, and here in Southern Hemisphere we work with both, but it's generally reported as Kg H2SO4, but in the Northern Hemisphere they work more to CaCO3, but it's all the same thing. There's a little factor you can use to change from one to the other, and that gives you all these parameters. You work out your acid-base accounting, which is your potential to generate acidity. And we have these nice little, there are plenty of graphs out there. I've just put in one example, but generally you would plot your net acid producing potential is your MPa minus your ANC, and you'd plot your net potential ratio as the ANC over the MPa. So that you can see is your MPa is 1, so that's saying that as much, you've got one component of it's in a 1-to-1 ratio, the acid producing as opposed to the acid neutralizing. And because pyrite weathers faster than the carbonates, then you're going to get an acidic solution. So Now, of course, there are limitations and assumptions in anything, and you definitely get some false positives because of the buffering by silicates. So we have the silicates in there, and in the lab we're saying, oh, we got these silicates, but in the actual field conditions, they're probably going to be weathering much, much, much slower than what we do in the lab. And so it isn't really providing that buffering capacity that we're hoping for. You can also get an overestimated buffering as well from the carbonates. For example, if you have siderite, actually it gives you no buffering capacity whatsoever. And so as I mentioned, you may need to also, in your tailings, when you get your sulfates out, it's reported in the total sulfur number. Now, if your MPA is based on that total sulfur number, but some of that was as sulfates, it's not going to be acid generating. It may release sulfate, but it's not going to be acid generating, and so that you also need to correct for that. And there are a few other, and I won't go through them all, it's there, but there are a few other things that bring in these limitations. For example, the titration, it's based on a fizz. I mean, it's a physical thing. It has improved, of course, but you add acid to your sample and you see how much it fizzes, basically. And I mean, what I think is fizzing a lot might be different to what you think is fizzing a lot. So there is some bias that can be brought in. So, yeah, and the laboratory results often use larger rinse water compared to the field conditions. So in field conditions, you'll have your secondary minerals having time to precipitate out, and here you just rinse the whole lot off. So you're actually going to miss some of the processes that are going on. So there's another test that we use to support the static tests, and that's a net acid generation. And it was brought in to reduce some of these uncertainties. And basically, you really just throw a whole lot of acid at it, hydrogen peroxide, to see whether there is some neutralizing capacity. And basically, if the NAG pH is less than 4, after you've done this, you've give it time to neutralize, then it's going to be potentially acid forming. But again, it's got some very limiting, there are some limitations. So I think the message is that never use these two on their own, use them together. And then we come up with a table which finally helps us to classify whether the samples or the tailing samples are going to be acid generating or non-acid generating or uncertain, based on some of these parameters that I've discussed here. And I won't go through them all, there are references, it's all very well known. Okay, and then we do the static leach test. So that's now we want to see what is the potential mobility of the trace metals. So where people sometimes go wrong is they think that you just get your leach out and that represents your drainage. No, it doesn't. It just represents the potential of how much can be released. And there are different types of leaches. We've got the distilled water leach and the synthetic precipitation leaching procedure, which sort of tries to simulate rain. It's slightly acidic, and then slightly different ratios. And those are used generally to compare to your standards. So I've got here an example. It was actually in the DRC. So, and every country has different standards. So these are considered the low risk, high risk tailings metals in DRC compared to our South African limits, which is the LC concentrations that we need for waste classification. Yes, some of them are fairly similar, but this is what we use the information for, basically. And every country that we work in, you've got to be very specific and know what am I going to be comparing it to. But always a nice general one to use is the IFC mining effluent standards, because everyone uses it. And of course, if you're going to get some possible exposure to receptors in some way or other, then the World Health one is a good one to look at as well, if there is possibility of it being exposed in drinking water. Okay, that's just an example of the South African waste classification of tailings. And it's so the results that we got from the leaches, the total and the distilled leach, those we use as our LC, and that's compared to some standards, which they're not just any old standards, it's actually the globalized, harmonized system of classification. And so it's an international standard. But based on whether you fall into, sorry, I keep going wrong screen, whether you fall into this category or that category, LC is bigger than TC, then it will guide you as to how risky the tailings is. And I mean, that's useful for any country. It gives you something to hang on to. But then you can take it further and build that in the inputs to your tailings designs is really, is it going to be acid generating? Is it a risk? And then that's linked to some barrier designs in South Africa. So, I don't know where I am on time. Okay, so the other test that we do is kinetic leaching, because as I said, the static tests don't give you any of the rates, how fast minerals are going to be released. It's just a snapshot in time, both the leach and also doing all that other ABA counting. So that's why we do this kinetic leach testing, which is generally run between 20 and 40 weeks. And that's to give you time-dependent data on the kinetics. And it'll give you the time to when your acid rock drainage generation could be onset. This one you can give as a better predictor of what your drainage quality is actually going to be. And the longer you run the test, the more reliable it is in terms of what you might get long-term. And this is usually used to calibrate the geochemical models, is the kinetic testing results. Oh yeah, and you can also try testing various treatment options just in the lab and then try and upscale it to field scale. So there are different ways. Again, there's a humidity cells test, which is very, very standardized. It has to be a certain amount of solid to liquid ratio, it's specified, and the conditions in the lab have to be kept standard. It's got a lamp, you keep it humid, because what you're trying to do is simulate your weathering process as fast as possible so that you actually come out with a reaction rate. And that's pretty standardized by all geochemists across the world, so you can compare this reaction rate to that. On the other hand, there's the leach column test, which I actually find more useful, because basically there's more flexibility and you've got more solid sample to the weekly rinse. So you're actually trying to simulate what's happening out in your pile of tailings outside there in a lab condition without to see which secondary minerals are going to precipitate, and that will give you your predictors of your mine drainage. And then there's, of course, a field test, and this is it's very time consuming, but it's actually really worthwhile to try and set them up, and that's where you set them up in big bins and you actually leave it in the natural conditions on the mine site. So if it's snowing or it's very hot or dry, whatever, and you keep collecting the leachate, and that gives you those results. So the last thing that I was coming to is the particle size, and it's been mentioned before. So generally, we'll consider that something is dissolved if you run it through a filter of 0.45. So for example, those leach tests are all run through a filter of 0.5 micromoles. But the graph I've got here, and this is sort of becoming a hot topic. Certainly, I was recently at the IIH conference in Davos, and people are this is a really hot topic, is what to do about this colloidal bit, which kind of falls in the cracks between real sediments and dissolved stuff. And I think the point I'm trying to make is, if you look at this graph here, some of these metals, in fact, a lot of these metals, are happier to be more attached to sediment colloid and in a colloidal form than some of the others which are more easily dissolved. So we take a sample of tailings and we filter it and we say, oh no, there's nothing there. But actually, if you look at the colloidal component, which actually can move off, I mean, this graph here shows so there's 1 micromole. We filter it there. So all of this stuff can still move off in pore spaces and fractures in the rock. So what we try and do, and I don't think it's totally effective, is to compare the total metals versus the solid, dissolved state. And at the moment, I'm trying to work out if there's a way you can filter it, because this is for the leach test. You know, could you actually then look at the colloids actually stuck on the filter afterwards? Because we are definitely missing something. So I think that's just about me. The closing remarks are that they're classified as to whether they're going to be saline, neutral, or acidic, and that's based on the metals and the ability to generate acidity or not. The mineralogy is very important. If you've got more carbonates and silicates that are weathering faster than your pyrites, then you're going to have an alkaline system. And if you've got more pyrites weathering faster than your carbonates and silicates, then you're going to have an acidic environment. Okay, and then you use those to determine your acid rock drainage potential and your metal releases. That's based on your static leaches and your kinetic leaches. Just a quick summary there. That's static, they've both got their place. It's quick and inexpensive, but kinetic gives you a lot more data as well. And then, yeah, your tailings risks are based on what you can leach out through there, and that can be provided as input to liner and barrier designs. And finally, yeah, the particle size. It's a topic that's being discussed really to try and understand how we're going to deal with this colloidal state, because sometimes it is more of a problem than anything else. And all of that into geochemical modeling, which I didn't have time for, but hope I didn't bore you with too much geochemistry.